Okay, good morning. So this is the third talk of my series, the last one. There's some technical material that I still want to convey, but I will also open it to talk about, answer questions and talk about directions of the current research, current challenges in machine learning. So let me start by recapping what we did in the last lecture. So I think the most important message is that we had this fundamental theorem, and the fundamental theorem tells you that all of those conditions are equivalent, as we've mentioned. The main thing is that we know that learnability, the question is whether a class is learnable or not, is completely determined by the question, by its VC dimension. If the VC dimension is infinite, then it's not learnable. If the VC dimension is finite, then it is learnable. And we will soon see also a quantitative version that shows that this relationship is even more tight. It's not just learnable, not learnable, but it also completely determines the number of needed samples. So, okay, and the main tool, I will not go, what we did see is that A arrows, B arrows, C arrows, and all the arrows go in this direction was kind of trivial, just follows from the definition. Except that A arrows B, that's something that we proved, that uniform convergence sufficient for ERM being successful. And the difficult part is going from having a finite VC dimension to showing that the class has uniform convergence problem. And the main tool for doing this will be the shatter function and the Tau lemma. So we said the shatter function is for every, we have a fixed class A, H, and for every M, we look at all sets, all subsets of the domain of size M, and for each of them we see how many behaviors H has on this set. So this is H behaving on A, and we count how many of those. So we count them, and that's pi H of M, and we said that it's always 2 to the M up to the VC dimension, but then it is below 2 to the M above the VC dimension. This is trivial. And the Tau lemma told us that above the VC dimension, it suddenly becomes polynomial. Polynomial with the VC dimension index. That will be the main tool, and I will soon explain how does this tool give us the main result. We also have a quantitative version, which is even more impressive. And this version says that if I have a class of VC dimension D, I can find constants that are independent of the class and independent of the VC dimension, such that the number of samples that I need in order to get uniform convergence. Remember, so this is the number of samples that I need, so that the samples of this size are delta likely, 1 minus delta likely to be epsilon representative for every element in H. So this number is completely determined by the VC dimension. You see, it is captured between the same expression just with two different constants. VC dimension plus log 1 over delta divided by epsilon squared. So the VC dimension up to constant determine completely the number of samples that I need for uniform convergence. And therefore, we can see that it completely determines the number of samples that we need for Planck learnability and completely determines the number of samples that we need for usual learning. So there are two things to take from these formulas. One is that the expressions on the right and on the left are exactly the same, and the only difference, this should have been C2. Yeah, of course, between C1 and C2. There are two constants, right? Not between C1 and C1. So the only difference is constant. The other thing to notice is that if you're doing agnostic learning, we have to divide by epsilon square. If we are doing realizable learning, we only divide by epsilon, which makes the realizable case much easier. So if epsilon for me is the precision that I'm shooting for is 1%, then divided by epsilon square means that I need 10,000 times the VC dimension in order to get such precision. 1 over epsilon square, where epsilon is 1%, is 10,000. So I need 10,000 times the VC dimension example. On the other hand, if it's realizable, then I only need 100 times the visit dimension example. So the realizable case is much easier if the realizable case means that our hypothesis class is really suitable for the data that we are trying to learn. Yes. Right. The constants are independent of anything. They are like something like 32 or something, the gap between C1 and something. It's very tight, and the tightness here, I mean, those results are old. They're from the work of Papnik and Chapolenkis from the 70s. This result here, there was some log factor that we didn't know how to get rid of, and we only managed to get rid of it 2 years ago. But anyway, everything is very. So that's one thing to note. I mean, two things we said, that the bounds are completely tight, and the agnostic case is harder than the realizable case. And the other thing which is important to notice is that this is, what do we mean by this sample? Sample size we mean a sample that suffices to learn regardless of the distribution. So those are in some sense worst case bounds. They tell me what is the worst case that can happen if the distribution is very kind of uninformative and the function is very far from being in the class H. The worst case is going to be these bounds. But in reality, it is often the case that we get better behavior. So those are, I mean, the lower bounds, they just say there exist hard cases that will require so many samples. The upper bounds are something very optimistic. It tells me under no matter what conditions, such sample sizes will always suffice. Yes.
Sorry. I asked, I said, like, I don't really get the same. Is a statement that these are equivalent, or is a statement that if H is uniform, like has this uniform converted property, then this holds?
No. The statement is if H has PC dimension D, then this is the sample complexity for uniform convergence. This is the sample complexity for learning the agnostic case. This is the sample complexity for learning in the realizable case. All of them just follow from having PC dimension. I'm not looking here at implications between those three states. The structure, the logical structure of it is that we have here PC dimension equal. The logical structure is that we just have PC dimension equal D, and it implies those three statements. So PC dimension of H equals D. It implies the sample, the rate for uniform convergence. It implies the rate for agnostic learning, and it implies the rate for realizable. Realizable. So the only assumption is the VC dimension.
So the assumption is that the PC dimension is smaller than infinity, right? So it's finite.
Yeah, but here we have much stronger statement because we see that it's not just a question of learnable or not learnable, but it also gives you the exact sample size. If you know that the BC dimension is 7 and you want to learn with precision 0.1, you know that you are going to need 70 examples.
And my problem here is that some H might not have the concept, right?
Not if it has a finite BC dimension.
Okay, that was my question.
So I'm saying if you have finite BC dimension, then you have this, then you have this, then you have this. Yes. Thank you very much.
So I was wondering if sample sizes they don't really check, right? Just some very different constants that share the same bounds.
Right. I mean, you know, if I had here and each of them has its own constant, I could take a strong enough constant, a small enough constant that's below all three on the left, and a big enough constant that's above all three on the right, and then I have the same constant.
But is it actually tighter
So what I'm saying is that it's not very important to find out the bounds because the bounds are anyway for the worst case distribution. So realistically, you never really need so many examples. Okay? But it means that the visit dimension is really an important parameter of a class. Yes? No, exactly. So that's a very good question, whether it's for the best algorithm or any algorithm. But what we saw in the previous slide is that ERM, the simplest methodology, which just find something that's in H that fits a database, test already gets the best bound. So in some sense, the most basic algorithm already gives you as much as you can hope to get. So we will need sophisticated algorithm not to save sample complexity, but to save computational complexity, which I will talk about later. Okay? So the conclusion is that the visit dimension is really an important parameter for learning. And how to compute the visit dimension? So let me just give you one rule of thumb. Of course, to compute the visit dimension for every different class is a challenge. We need to show a set of this size that's shattered. We need to prove that no larger set can be shattered. But there is a rule of thumb. And the rule of thumb says that the visit dimension of a class is often equal to the number of parameters that you need to set in order to specify a specific hypothesis in your class. So think, for example, of initial segment. How many parameters do I need to set in order to pick a single initial segment? Just one, which is the threshold. And indeed, the visit dimension is one. If I want to look at the class of intervals, how many parameters do I need to specify in order to pick a specific interval? Two parameters, the left-hand side and the right-hand side. And the visit dimension of the class of intervals is 2. If I want to look at rectangles, say in RD, how many parameters do I need in RD to define an axis-aligned box in RD? I need 2D parameters, top and the bottom in every chord. And the visit dimension is indeed 2D. And the same for half space. If I want to define a linear partitioning of the space, I want to define this linear subspace, then what I need is how many parameters do I need to define a line in R2? 3 parameters. And to define a linear half space in Rn, I need n plus 1 parameter. And the visit dimension is indeed n plus 1. So as a rule of thumb, it is the number of parameters. And this turns out to, I mean, it's not a theorem because I can't design, classes that will violate. I'll take the class of all intervals and delete some of the intervals just to kill the visit dimension or something like that. But the rule of thumb turns out to be, the reason I want to mention it is that I think we are all nowadays very curious about deep neural networks. So I can ask, what is the visit dimension of deep neural network, of a neural network in general? So if I'm not going to talk to give now an introduction to neural networks, so just assume that for those that know what they are, so it is some kind of it's a function that you take your data, so you have your x, which is the vector, say x1 up to xn, and you have your network, and you feed your inputs to the network, and then you have gates here, and so on. And at the end, the network computes some output, right? And now if we apply the same rule of thumb and ask, what is the visit dimension of the class of neural networks? So you fix an architecture, you fix the architecture of the neural network, and when you tune up, when you train the neural network, what you actually do is you figure out what should be the best weight. So every edge here should have a weight, and the training of the neural network, after you decided on the architecture, which usually you do based on prior knowledge, you train the neural network to find the best weight. So now if we go back to this rule of thumb, how many parameters do I need to set in order, if I fix the architecture, and now I look at the class of all neural networks with this specific architecture, with so many nodes, with these connections between the different layers, how many parameters do I need in order to pick a specific function? The number of weights, right? The number of weights or the number of edges. And indeed, it turns out that the VC dimension of a neural network is roughly the number of edges times log the number of edges. So it is roughly really the number of parameters that I need to set in order to determine the neural network. So the larger the neural network, the larger the VC dimension. And also, if we go back to the previous slide, so then the number that I need to determine neural network is the number of edges, and that's roughly the VC dimension. And if we go back to the previous slide, and we want to know how many examples do I need to train a neural network, then what you see here is that I was trying to click on this, but it doesn't do anything. So what you see here is that you have in denominator, you have the VC dimension. And in denominator, I can ask, what is my precision? I can take epsilon out and put m below, right? So I can say, what is the error that I'm going to make? What is epsilon? So I can move epsilon here and m to the denominator. So I have that epsilon is roughly the square root of d over m. M is the number of samples, which means that if the number of edges in your neural network is in the order of magnitude of the training data that you have, then you can get no guarantee of performance. So what I'm saying, if we just look at this formula and we just want to see what kind of error do we get, we see that the error is roughly, that the error that we get behaves roughly like square root, and here I have the VC dimension of the neural network, and here I have the number of examples, the sample size. So if the number of edges in your neural network is the same order of your training sample, then this behaves like 1. All the guarantee that you get is that your probability of making an error will be at most 1, which is not very useful. So when we're using very big neural networks, if we want to rely on such guarantees, we need to have sample sizes that are much bigger than the number of edges in my neural network, or much bigger than, well, the number of edges is a good estimate for the VC dimension of the neural network. And it turns out that in reality, I'll talk about it at the end, people are using very deep neural network on data which is not big enough. And how do they survive? How do they get results? It goes back to the point that those bounds are worst case. Those bounds are worst case. It means there are situations under which you will fail if you use only so few examples. But it doesn't mean that you are bound to fail under anything. It just means I cannot give you guarantee. You may get lucky and do well, but I cannot give you guarantee. There could be some bad distribution that will completely fool. Okay? So it's important to see that there is this very tight relationship between the VC dimension and the exact number of examples that I need in the bound. So, okay, I wanted to move on, but before that, let me just give you one hint on how do we prove this theorem. How do we prove the theorem that if you have a finite VC dimension, then you can learn? And as I said, the crucial point is the Sauer lemma. And the idea is, as you remember, in the first lecture, we showed that if you have a finite class, if the class is finite, then you can use the union bound. You just ask, how many candidates do I have? If the class is finite, then we know that the number of examples, it is color clear enough, or should I use something stronger? Okay. So the number of examples that I need for a finite neural network was roughly log of the size of H plus log 1 over delta divided by epsilon squared. And we got this log because we did a calculation of how many examples I need to zoom in on the error of a specific H. And then I counted all the possible H's and took the union bound. So this came from the union bound. I took the union over all members of H. Now, how does it relate to the Sauer lemma? Now we are talking about an infinite class. And if I take log of h, it will be infinity. It will not give me anything. But the Sauer lemma tells me that if I have a sample, and I want to pick an h that behaves nicely on the sample, so I just want to pick among all the behaviors on my sample. And the Sauer lemma tells me, what? Okay. Oh, the people in the other room are complaining? Okay. So what I'm saying is that using the union bound, we got that the number of examples that I need to learn epsilon delta, a finite class, was roughly log of the size of h plus log 1 over delta divided by epsilon square. And I said this part came from how difficult it is to estimate the error of a single h. And this part came from taking the union bound over all h's in my class. I want to have a sample that will successfully estimate each and every one, so it's end, and that's what I get when I do the calculation. Now I have an infinite class. I have an infinite class, but I have a sample here, and the sample says contains at most m points. And I want to consider all candidates of which of the hypotheses for my class am I going to use. So in effect, I don't really have to use all the possible members of the class. I just have to take one representative for every behavior on my sample. Because all I care about, if I want to calculate my empirical error, to do empirical risk minimization, all I care about is how it behaves on the sample. What is the empirical error? And the Sauer lemma tells me that even if the class is infinite, if it has finite VC dimension, and I take a sample of size m, the number of behaviors on this sample is going to be just m to the d. So the effective size of h, if I take h and restrict it to the sample, is roughly m to the d. So if I take log of this, what I'll get here, instead of the log of h, I will get something like d log m. So let me just raise it. So what I'm saying, the Sauer lemma tells me that the number of behaviors on the sample is at most m to the d. So this is the effective class that I have to choose among. So I take the log of this number. So I get that m of h epsilon delta, the number of examples that I need, is at most, and now I take a log of this guy. So I get here d log m. And that's roughly the way we get those bounds. D log m plus the log 1 over delta divided by epsilon square. But notice that now, if I try to calculate epsilon, my error, if I try to calculate my error, I get something like the square root of d log m divided by m, epsilon divided by m. So as m goes to infinity, this goes to 0, and my error goes. So this is the idea why the Sauer lemma gives me learnability of classes with finite VC dimension. It tells me that if the class is finite VC dimension, the number of behaviors of the sample is only polynomial. So when I take the log, I get here log m divided by m examples. The error will go down as m goes. Okay, so that's basically the idea behind the proof of the connection between the VC dimension and learnability. It's the last, the E implies A in this slide, right? Oh, come on. My pen is clicking. Oh, right. So it's the E implies A. Why does the VC dimension suffice for uniform convergence? Okay, so that's the connection. That's the connection of the Sauer lemma. Why the Sauer lemma is the critical component in my proof. The number of possibilities. And if anybody of you heard about the Rademacher complexity, So the random microcomplexity is roughly the same thing, but we look at the number of behaviors that are relevant to the underlying probability distribution. But I will not get it. So this is the main idea. Okay, so we can move on. We have the main theorem. We know of the importance of the main. But if we look at this, one can think the story is over. If I want to learn something, all I need to do what is the visit dimension. Once I know the visit dimension, the ERM algorithm, the simplest algorithm, will already give me optimal sample bounds. So I will run ERM, and I'll go home, and there is no industry of people getting ridiculous salaries for machine learning. So what is still missing here? So there are two components at least that are missing here and they are crucial, and that's what I want to talk about next. So where are we? Okay, we're here. So there are two components that are still missing. One component is that classes are learnable only if they have finite visit dimension, and this is a very limited family of classes. So for example, if I want to use deep neural networks, and I want to see if I cannot learn with a certain depth, I will increase the depth, I will increase the number of neurons in my networks. If I cannot learn, say, with half spaces, or I want to know if a patient is at risk or not, so I can take two parameters, the blood pressure and the heartbeat rate, and see if it gives me good results. If it doesn't give me good results, I will take more parameters and more parameters and more parameters. And the visit dimension, if I allow myself this flexibility of increasing the number of tests that I do to my patients, the visit dimension just keeps growing and growing and growing. So fixing the class with a finite visit dimension sometimes is not sufficient. Or another way of looking at it is you saw that the expressive power of linear half-space is very limited. It only gives me a small fraction of all possible partitions. So maybe I don't want to just use linear partitions, but I also want to allow polynomial partitions of any degree. And suddenly my class will blow up and will not have finite visit dimension. So my first concern is that having a finite visit dimension may be too limited. And the question is, can we do anything about it? Because we have a theorem that tells us you are learnable if and only if you have finite visit dimension. So what can you do if you feel that finite visit dimension is too limited? The other big elephant in the room is the computational complexity. It is crucial that we do our calculations fast. And the computational complexity of ERM, in many cases, it's anti-hard. So if you need 10,000 examples, the runtime to find what is the best hypothesis over those samples of 10,000 examples, you can get 10,000 examples, but the runtime is going to be exponential in 10,000. So you will need a calculation of 2 to the 10,000 just to go over your hypothesis and figure out which one is best, which one is ERM. So this is a very crucial component, the computational complexity, and the other one is the limitation to finite visit. So these are the two topics that I still want to talk about in my remaining time. Is there any question at this point? Okay, so how can we handle the issue that finite visit dimension is too restricted, and on the other hand, we have a theorem that tells you can learn only if you have finite visit dimension, right? So this is a lesson that I learned from my supervisor. When you have a question that's too hard, change the question. So the trick here is that we relax the notion of learnability. So we relax the notion of learnability to something which is still of practical value, but will give us more leeway. And the notion is non-uniform learnability. So what does it mean, non-uniform learnability? See what is now being different than what we had in the PAC sense. What I have here, just like the PAC, I said a class is learnable if there is a function, but now suddenly the function is different. What is different in my function? It not only takes the parameters epsilon and delta into account, but it also takes h into account. So this reads exactly like what we had in the usual Park learning, except that my number of examples that I'm allowing may depend on H also, not just on epsilon and delta. So if you remember the way we described agnostic learning. Agnostic learning, we say, I want to be able to compete with the class H. I want to be able to do as well as the best in H. Now I'm telling you, you want to compete with the class H. For any member there, I will allow you a number of the examples that depend on this member. So if I want to invest your money and give you a promise, I can do as well as any broker in this big investment company, then I can give you here a more sophisticated bound. I'm telling you, if you want to compete against this novice broker, I don't need many examples. But if you want to compete, if you want me to compete with this big expert, I need more examples. So now I allow the number of examples to also depend on the age that I'm competing. So just to compare what we had before, if we looked at the agnostic learning, the requirement was the requirement for successful agnostic learning was that the probability, I'm trying to write it as similar to this as possible, of the loss, the true loss of what my algorithm spits out when it has the sample S is at most, and what I had here is the minimum over all H in H of LP of H plus epsilon. We said that the probability of this event, should be greater than 1 minus delta, or failure of this event. So this was our agnostic learning. Now notice that I'm doing exactly the same. Instead of writing here minimum over all H's, I'm telling you for every H, you will be able to compete with this H. So you are able to compete with the minimum over all H's, but for each H, you may need a different number of examples. So that's the relaxation that I'm allowing. So we are competing with the best H in H. But for everyone that you want to compete with, you tell me who do you want to compete with, I'll tell you how many examples you may require. It doesn't trivialize completely because we're still having this guarantee regardless of the probability distribution. This number, this function, is determined for once and works for any probability distribution, for any labeling, whatever. So I just need to know who I'm competing with. I don't need to know what is the data like. Okay? So this is the relaxation that we call non-uniform learnability. Non-uniform because it is not uniform over the whole class H. For every H in H, I allow a different number of examples. So what do I gain now by switching to this notion of non-uniform learnability? Is the step clear what I did here? So what, yes. Yeah, do we have, where is the microphone?
So the question is, we said that we can still with the best H.
Right, because for every H, I compete with this H.
Right, but isn't then that sample size that I need so bound on the sample sizes I need for all other products, and by that I have
Okay. So what you're saying is, okay, why make it so complex? Pick the best H. See how many examples you need for the best H, and that will be good for all other H's. Why do I need such a complicated definition? It's a very good question. Anybody has the answer? No, there is a best, but the best changes from one distribution to another. And I want a bound that is fixed for all distributions. So, you know, the identity of the best may switch between the distribution. Different function that I want to predict, a different H will be the best. Right? And I want the bound to be independent of the distribution, because the distribution is something that I don't know. I mean, I can tell you in advance that no matter how the markets are going to behave, if you want me to compete with her, I need 1,000 examples. If we want to compete with him, I will need only 10 examples. But this is regardless of how the markets behave. If I want to determine who is the best, it will change all the time.
But how is that different from the setting with before? So there we also have the
right. It was a more demanding set. But before, I didn't even allow you to depend on H. We just said M of epsilon delta. It was a stricter requirement. Here, with every different probability distribution, it may bring me another H to the front, and I'll look at this H and tell you how much I need.
And I'll still take the infimum over all those.
Right, but it's not the infimum, it's the supernumum. For every distribution, there's going to be an H. For every H, there's going to be this number. The class is infinite. If the class is finite, it has finite this dimension. The class is infinite. If I try to take one bound for everybody, it will be infinite. Okay? But it's good that you ask these questions because this is really kind of a complicated definition. But this definition turns out to be what is really working in practice. Not that the practitioners are aware of this result, but this is the justification that we can provide. It's not just a justification. The algorithm that comes out of it was the structural risk minimization, was proposed by Vapnik, and this is the key for most of the stuff that we're doing. I'll talk about it in. So it's really one of those areas in which the theory was the front runner and the applications just caught up later, although they don't need to know the theory, just need to know the process. So what is the result that I get here? So here I get a very nice new characterization. A class is non-uniform learnable if and only if I can decompose it into a sequence of classes, Hn. For every n, I will have a class Hn, such that each Hn has uniform convergence, and H is the union of all of them. So a class, now I'm not necessarily requiring you to have a finite least dimension. All I require is that you are going to be a union of classes such that each of them has finite least dimension, but the number of these classes can be infinite. So for example, I wonder if I put a slide with these examples. Right. So here is the example I wanted. Say I want to compete with the class of all polynomials. So what do I mean by the class of polynomials? So if I have a polynomial P, I look at the label 1 whenever I substitute x in the polynomial and I get a positive result. So polynomials give me more flexibility than linear functions. And the higher the degree of the polynomial, the more flexibility do I have to determine where it's going to be positive and where it's going to be negative. But if I look at the class of all polynomials, the VC dimension of this class is infinite. However, I can decompose it to a countable union of classes that each of them will have a finite VC dimension. So, anybody of you can offer me the decomposition? If I want to handle the class of all polynomials. So, maybe first thing we need to do is to make sure that everybody understands what I mean by class of polynomials. So, right, look at this definition here. I said that for every polynomial P, HP is the hypothesis that gives me 1 whenever this x substituted in the polynomial is bigger than 0. Right? So if I look at degree 2 polynomials, I get 2 sets on the 2 sides of the valley of the quadratic function. If I have a third degree polynomial, I get more sets. It gets more and more complex. So in this class, if I go over all polynomials, it has infinite VC dimension. Anybody has an idea how can I decompose it into a union of classes such that each of those individual classes will have only finite VC dimension? Yes.
You could take the union of all polynomials of degree up to D.
Right. Very nice.
Do a union that.
Right. So what I can do is I can say the class of all polynomials is the union. So this class H of all polynomials is the union over D goes from 1 to infinity of HD where HD is the class of polynomials of degree at most D. So each of those classes has finite basis dimension. And it is not difficult to see that each of those classes has a finite basis dimension determined by D. It's like D plus 1. So I can take the class of all polynomials and represent it as a union of classes, each of them of a finite basis dimension. And therefore, by the previous theorem, the class of all polynomials is non-uniformly learnable. So I can say I can compete with any polynomial prediction. But if you tell me what is the degree of polynomial, I'll tell you how many examples I need to pick. Okay? So it gives me new flexibility that I didn't have before. Now I don't need to determine the degree of the polynomial in advance. It will just be a factor affecting my sample complexity. Okay, so this is the first example of the advantages that I get by relaxing my definition to allow the non-uniformity. Yes? How do I know the degree of the unknown function that I'm trying to estimate, right? Yeah, so I don't know. But what I'm saying is that I see how many examples you can give. You tell me I can give you 1,000 examples, so I can tell you, okay, so the guarantee that I'll give you is that I'll be able to compete with any polynomial of degree most 1,000. If there is a polynomial of degree most 1,000 that does a good job, I will do it. So you can view it as saying, tell me how many examples you have, I can tell you with which h's I can compete. Okay? And we will see later that it is not only this kind of statement of guarantee, but it also drives an algorithm, which is the most important part. We will see the algorithm. Okay, another example is the class of all finite subsets. Remember, we talked a lot last time about the class of all functions that give at most finitely many ones. Again, the class has infinite basis dimension, the class of all functions that assign 1 to at most finitely many points. How can I decompose it into a union of classes of finite BC, each of them? Similar idea, limit the number of points. So let HD be the class of all functions that give 1 to at most D points. Then I'll take a union of all these, and I'll get all possible finite functions. So again, this is non-uniformly learnable, and also the class of all finite unions of rectangles. So you can say, maybe it's not inconceivable that if I try to figure out what is a good characterization of say I'm again talking about patients, and I want to know what is a healthy patient. So I can tell you a healthy patient is either living in this rectangle, which is, say, this is the height, and this is weight of my patient, and this is being healthy or fit. But I can say there's not only one type of healthy people. Maybe these guys are also. So I have here the class of unions of two rectangles. Maybe my class decomposes into, right? Now I can ask you to have the class of all finite unions of rectangles. And again, it will have a non-uniform convergence, non-uniform learnability, because I can decompose it by fixing each time a higher and higher and higher number of vectors. Okay, so it gives me more flexibility, the non-uniform learnability. So what is the next obvious question to ask if you put yourself in a position of a mathematician? What will be the next question to ask now? What? Uncountable, or in other words, I mean, maybe everything trivializes. Maybe now with this new notion, everything is learnable, right? And then again, we are out of business because there's nothing to calculate, there's nothing, everything is learnable. Well, luckily for us, it's not the case. So it turns out that if H shatters an infinite set, then it cannot be represented as such a union. Remember that H can have VC dimension infinity by shattering larger and larger and larger finite sets. It can also have VC dimension infinity by shattering an infinite set. There are two types of infinite VC classes. Either you shatter, like, if you look at the set of all polynomials, you can shatter larger and larger and larger finite sets. You cannot shatter an infinite set. If you look at a set of all functions that give at most finitely many ones, you cannot shatter an infinite set, because to shatter an infinite set, you will also have to handle the partition that has infinitely many ones and infinitely many zeros. And you don't have such a function. But there are, of course, the class of all functions over the natural numbers does shatter an infinite set. Which set does it shatter? The class of all functions over the natural numbers. Which infinite set does it shatter? If I allow all functions over the natural number. Yeah, all natural numbers, of course, because I have all functions at my disposal. So I can do any partitioning of the natural numbers. So if a class shatters an infinite set, it is not such a union, and we cannot learn it even in this non-uniform learnability. Okay? So it is not, it doesn't trivialize. It is still an interesting collection of classes. All the classes that are non-uniformly learnable, it's not able. Let me make one more comment, which is not on my slides. When we talked about the non-uniform learnability, we allowed ourselves, I need this. We allowed M to depend on H and epsilon and delta, but we wanted this number to be fixed regardless of the distribution. What happens if I go even one step further and I allow myself to have this number depend also on the distribution? What will I get then? It's a further relaxation. I allow you not only to depend when I ask you how many samples are you going to need. It's not only that you will tell me what is the precision that you want and who do you want me to compete with, but you can ask me which distribution do you want me to compete with. How distributions will require more samples. If I allow this number to depend on P also, I get a notion which is called consistency. This is a notion that is favorable by statisticians. They talk about consistent estimates. Consistent estimators are estimators that as the sample size will go to affinity, they will eventually converge to a true good value. But you don't have any finite bound. It just tells you, depending on the underlying distribution, we don't know what is the underlying distribution, the number of samples that you will need eventually will be good enough. But you don't know until you get there. And so consistency is the next relaxation, allowing us to depend only also on P. And that's a notion of consistent estimators in statistics. But this is, in some sense, it's a vacuous node. Now everything collapses. So if we talk about consistency, then every class over a countable set is learnable. And the learning algorithms is just memorized. So what is memorized? You look at all the examples that you saw so far. If you see an example which is one of those that you already saw, you know what the answer is. If you see an example that has not been there before, you just say 0. Now, this is consistent because eventually you will see more and more and more and more examples, and the probability of encountering an example which is unknown to you is going down. So if we relax it further and allow the number to also depend on P, we get a vacuous notion, which is consistency, which is still a notion that is discussed a lot in statistics. But it is not useful in the sense of designing algorithms, because the simplest algorithm, just memorize, always gets you consistency if the domain is counted. Okay, so we are with the non-uniform learnability. I was trying to convince you this is an important notion, because now we're going to have a little bit of technicality to come up with good algorithms for this. Okay. So I want to prove this result. what result do I want to prove? I want to prove the result that the class is non-uniformly learnable if and only if it is a union of countably many classes, each of which is a finite VC, or each of which has uniform content. Right? So we have this equivalence, if and only if, that you want to prove. We say, on one hand, H is non-uniformly learnable if and only if I can represent H as a union of HNs, and N goes over the natural numbers, and each of those has a finite VC dimension. So I want to prove this characterization. Now, the easy case is to show that if it is learnable, then I can decompose it like this. So this is the easy case, and that's what I'm showing here. If it is non-uniformly learnable, then I can get such a decomposition. So this is the direction that this slide argues. And the idea is, so I have a class. All I know is that it is non-uniformly learnable. All I know is that I have this function m, the sample size, that depends on epsilon, delta, and h. So now I have to come up with a decomposition of my class. I don't know anything about my class. All I know is that I have this sample size function. So I will use this function to get my decomposition. So what I get is that I will define a class Hn. I will define the class Hn to be all those h's such that when we put here those epsilon, magical epsilon delta that we have for the no-free lunch theorem, I need at most n examples. So I look at all the h's such that if h is here, and I put these epsilon and delta parameters, I can handle it with at most n examples. So now I need to show you two claims. First of all, is that the union of those classes will give me all of my h. Why is that the case? Why is the union of all of those HNs, why will it give me the full h? Yes. Pause. Right. So it's non-uniformly learnable, so we know that for every h, I have this number, m of h, epsilon delta. So for any h in my class, it will fall in one of those HNs. If you give me an h in my class, I'll calculate the function. I'll tell you in which level of my decomposition it sits. So it gives me the whole class. Now the next argument that I need is why is each of those classes of finite VC dimension? So why is each of these classes of finite VC dimension? Any new participants? I already gave you a hint 2 minutes ago when I explained why did I pick these funny parameters here. What? The no-free lunch theorem. Because the no-free lunch theorem tells me that if I had an infinite VC dimension, then I will not have such a bound. Because Hn has a fixed bound. Hn needs only n examples in order to do this epsilon delta. And we know that if your VC dimension is infinite, then no bound suffices to learn with these parameters. So each of these classes has finite VC dimension. The union is all of my class. So we got that if the class is non-uniformly learnable, then it is such a union. Now we want to get in the reverse direction. Okay? We want to say if I can decompose it like this, then I have non-uniform learnability. And this is the interesting direction because this is the direction that will give me the learning algorithm for such classes. So as I said, those are very practical classes. This is the class of all neural networks regardless of the depth and the number of nodes. This is the class of all polynomial predictions regardless of the degree of the polynomial. So this is the classes that we really use, or the class of all SVM learners regardless of the kernel. So this is what, if any of you ever try to learn with an SVM software package or something, then you can have polynomial kernels or Gaussian kernels, and you can change the kernel until you get good results. So actually learning over a family of kernels, and it has this kind of non-uniform learnability. It has infinite business dimension. So the other direction is the more interesting because it gives us the algorithm. So let's just briefly go over it. I know that we are getting a bit tired of the notation. So I'll go more quickly, just to give you basic flavor of what is happening here. So in order to go in the other direction, I need to define the notion of a weight function. And a weight function is kind of a function that tells me how much importance I give to every level in this hierarchy. So my class is decomposed into these HNs, and I can think of it as if it is kind of an onion, not a union, but an onion. So here is my class, and it looks like an onion. Those are the HNs. And I want to tell you with these WNs, how much weight do I assign to each of them? Or in other words, if you want to think of it from the point of view of prior knowledge, or the point of view of Bayesian learning, maybe some of you have encountered Bayesian learning, it is how likely I think that the good hypothesis is going to sit in this class. So for every class, I give you a weight of how likely I think it is. And those weights, I want them to sum up to at most 1. I want to be able to interpret them as probability. What is the probability that your good hypothesis will fit in the class HN? So I pick a weight function, which is just a function that over all n's sums up to 1. And here are 2 examples of natural weight functions. I can take 1 over 2n squared, or 6 over pi squared n squared. Or I can take 1 over 2 to the n. Each of them, the sum over all n's is at most 1. So I can pick weights. They have to be decaying because I need the infinite sum to be bounded, but they can decay in polynomial rate, or they can decay in exponential rate. I can pick how well they decay, and I can also pick which classes are coming in the front and which classes are being pushed to have very low weight. Okay, so I pick such a weight function. And picking such a weight function gives me a handle on an algorithm on how to do it. So now we define. Now, this is kind of a technical definition. I define epsilon n of m delta as the best epsilon that I can get with m examples in the class Hn. So it's getting a bit too technical. If you don't follow now, it's not the end of the world. I will wake you up and tell you this is important now. Follow, okay? So now I'm just reversing. Usually I did m of epsilon delta, and here I'm looking at epsilon of m and delta. I'm just changing the roles in my functional dependence, and it has this parameter n because I'm talking about the class Hn. And with this, I can prove the following result, that if the class is non-uniform learnable, and I decompose it into HNs and gave you weights that sum up to 1, then for every H, the true error of H is at most the empirical error of H plus the smallest epsilon that gives me that I can handle with this number of examples and take into account the weight. So again, the formula itself is not so important. What's important here is suddenly I have a guarantee on the gap between the empirical error and the true error over a class of infinite Visa dimension, over a class that's non-uniformly learnable. And the extra component that I have here depends on where H sits. If H sits in Hn, then the extra component is this epsilon n. So it depends. For every H, I can bound how far is the true error of H from the empirical error of H. And the gap depends on the level in which H sits and the weight that I gave to this level. So I have a bound that says if H is sitting in a very low level, then the gap between what I see and the true error is small. If it is sitting in a high level, then the gap may be much larger. And this drives an algorithm. So the algorithm is going to be pick an H that minimizes this bound. You see, this is what we are shooting for. We are shooting for a small error with respect to the unknown distribution. We have this bound. So we can say pick an H that minimizes this bound. So this is the SRM structural risk minimization algorithm, and it's a very important algorithm. So SRM, or structural risk minimization, you have a class H. The class H is non-uniformly learnable. How are you going to learn it? You're going to take your class and decompose it into Hns, and you're going to pick a weight function, W. And now that you did this, you have this bound on the true arrow. So you are looking for an H that will minimize this bound. What did we do with ERM? Which components here were existing in the ERM principle, in the ERM algorithm? What did we minimize then? The empirical error, right. So when we did ERM, we only minimized this guy. We looked for an H that will minimize the error over the sample. Now I'm saying I'm minimizing this guy, but plus a penalty. If the class in which H lives comes high in the hierarchy, I'm giving it a big penalty. So now I'm trying to minimize not just the empirical error, because just doing the empirical error on an infinite VC class will give me overfitting, but I'm minimizing a sum of the error, empirical error, plus a penalty on being complex. If the H lives in a high Hn, I consider it a complex H, and I give it low probability. So think of it as it's a very basic principle in scientific exploration. I'm saying I'm looking for a simple explanation that will explain all my data, but I'm looking for an explanation that explains my data well, but I give you penalty if the explanation becomes too difficult, too complex. What? It is exactly regularization, exactly the principle of regularization. So I'm saying if I just wanted an explanation that is very low empirical risk, I could just make a list of everything in my sample and tell you if you're this point, you're 1, if you're this point, you're 0, if you're this point, you're 1. This has 0 empirical error, but it's a very complex hypothesis. And complex hypothesis will get penalized here, and I'm willing to sacrifice accuracy for generating a simpler hypothesis. And we will see it formally in a minute. So this is the SRM algorithm. It's a very important algorithm. And what still left to be determined is how do I decompose my class and how do I pick the weights. And this is going to be done based on prior knowledge. So here are so the resulting bound is that the number of examples that you need is depending on your epsilon and the n from which your hypothesis came. And here are some examples of how are we going to do such decompositions and how are we going to determine the weights. So this is exactly the principle of regularization. We look at the empirical error and add the penalty. And the penalty depends on how complex is the H. And I can come up with different notions of complexity. I can talk about the norm of a linear classifier. This is just to people who worked with linear classifiers. You know that we have penalization over the norm of the classifier or regularization. Or description length. I'll talk a little bit more about description length in a minute. I give advantage to short descriptions, and I'm willing to sacrifice error on the training sample for getting a concise description, a concise theory. Or it could be small margins, or it could be low prior likelihood. If I have in advance a notion of thinking which explanations are plausible and which are not plausible, so for a plausible explanation, I'm willing to pick it even if it makes some error. If you want me to pick an explanation that initially look implausible to me, I will need more supporting evidence. I will need to really see that it behaves perfectly wonderful on big samples before I will agree to an explanation that initially I thought is unplausible. So this SRM algorithm minimizes sum of the empirical error plus a penalty can have many different manifestations depending on your prior knowledge about your problem. So what I want to talk about, the last thing I'm going to talk about in some slides is the notion of description length, because it's a very interesting notion. Description length as my notion of penalty. So I'm going to pick a description language and say I prefer things that can be described concisely over things that need a lot of explanation. So here is the definition of description length. So what is the description length? I have a class of hypotheses, and I have to pick a language to describe my hypothesis. So we are doing computer science. At the end of the day, every description is just a binary, a string of zeros and ones. So picking a language, a description language, is picking a function that maps every h to a string of zeros and ones. So every explanation, I will encode it as a string of zeros and ones. And the only requirement from this language that I impose is that it is prefix-free. So what does it mean, prefix-free? Is that no description of H1 is a sub-description of H2. It is like I want to describe each H by a program, and no program is a substring initial segment of another. Because if I read my program, I get to the point where it says end of program, and I will stop reading. So no program, if I look at the language, any programming languages, any program, I mean, if I look at this as the descriptions of the function, the program, they are prefix-free. No program is an initial segment of another. Okay? So I demand this prefix-freeness, but otherwise I can pick my programming language as I wish, or my description language as you wish. So you can think of it as a programming language. For every H in H, I pick a program that describes it. And it's prefix-free, that's description language. Okay? And now it turns out that if I have such a collection of strings, which is prefix-free, I have what is called Kraft's inequality. What is Kraft's inequality? It says that if I have a collection T of binary strings such that none of them is an initial segment of another one, it's prefix-free, then the sum of 2 to the minus the length of sigma is at most 1. Let me just, I know that I'm stretching your patience maybe too much. So let me just explain this point, and then we will go to conclusions and some open discussion. So what I'm saying is that, you see, if I pick description, so I can say, I can describe all my language in a tree. Here is the empty string. Here is the string which is only 0. Here is the string which is only 1. Here is the string 0, 0, and 0, 1, and 1, 0, and 1, 1, and so on. What does it mean that I pick my language to be prefix-free? It means that I cannot pick two descriptions that one is sitting under the other. So I'm going down a branch, I pick a description, say this is going to be one of my descriptions of my program, this is going to be a program. It means that anything below it is not a program. Right? In such a case, I claim is that the sum of 2 to the minus the lengths is at most 1. Because, you know, one way is to say these are my two descriptions. So what will be the sum? A half plus a half is 1. I can pick all my descriptions here. So it will be a quarter plus a quarter plus a quarter plus a quarter, it's 1. But the Kraft inequality says no matter how deep you go in which branches, you will always have this property that the sum of the exponents of the length is at most. Now, why do we care about it? Because this sum that is being at most 1 tells us we can use it as weights. Because remember, we needed to pick a weight function such that the sum of weights over all n's is at most 1. So I can pick as a weight for my hypothesis if my class looks like a sequence of hypotheses. I can decompose it into classes that each of them has only one hypothesis in it, and pick the weights to be the description length. And I know that these sum up to at most one, so I can take any countable class of hypotheses, have a language that will describe them, and use my structural risk minimization. And what I get is this algorithm that tells me pick an H that minimizes the empirical error plus the square root of its description length plus ln 1 over delta divided by 2m. So notice what we got here. What we got here is that an algorithm that says pick a language to describe your hypothesis. And now when you see the sample and you want to pick what do I predict with, I want a hypothesis that has small error but also small description. For a shorter description, I'm willing to sacrifice error on the sample. So this is kind of a formal proof of a very important principle. Anybody knows what's the name of this principle? Yes. It's the Occam razor. Occam razor tells me you should always pick an explanation with short description. But usually people view Occam razor as a philosophical, soft kind of advice, heuristic. Here we have a proof that it really works. You have, if you want this algorithm to have guarantees of success, you need to pick a hypothesis that minimizes the error plus the square root of its description length. So for short description lengths, we are willing to sacrifice errors. And it not only that it supports the Occam razor principle, but it also shows you something very interesting, because this bound holds regardless of what your description language is. So you can say, should I pick H1 or should I pick H2? Maybe according to some language 1, H1 is shorter. But according to a different language, H2 is short. Right? Even if I compare words in English and in German, the length of, I can compare two elements and look at the German word and the English word, maybe the order of which of them has more letters changes. And the theorem that we have says it doesn't matter. No matter which language you pick, as long as you picked your language before you saw the sample, this principle will work. So there's something very nice here, which tells you, pick your language as you wish. But now stick to your language, you get a sample, try to find something that has low error plus short description. Right? If you pick a bad language, all those with short descriptions are going to have a lot of error. If you picked a good language for your problem, then you will find someone that combines having a short error, a small error with a short description. Okay? So that is the very important principle of minimizing the description length. But you have to realize that it has a parameter which is completely free, and that's my description language. Okay? So I think we have only 15 minutes left, and I don't want to get more technical. So I will stop using my slides here and just mention that there is one big component that we didn't talk about, and this is the computational complexity. So all of those algorithms, the structural risk minimization or the ERM, in most cases they are NP-hard. And the struggle is to come up with algorithms that work well in practice. But optimization is very difficult. So this is another completely different aspect of machine learning, and this is how much computation. Now that you have enough samples, how much computation will you need to invest in order to come up with something useful? So I just don't have to get time to get into it, but that's a big component of machine learning, the computation time. What we did in this tutorial is just talk about the sample complexity. And the conclusion is, VC dimension is crucial. Classes with finite VC dimension can be learned with bounds that are independent of anything. If you want more complex classes, like the class of all polynomials, you have to switch to non-uniform learnability, or the class of all countable functions. You see, what this allows me to do is to learn the class of all possible programs. If I want my predictor to be a program, I can learn the class of all possible programs. Because all possible programs, each of them has a description, which is the program, right? So I can do non-uniform learnability over all possible programs, and this principle just tells you pick a program that predicts well on the sample, but is also short. And you are free to pick your programming language in advance. Doesn't matter which program. Okay. What? It's not a program because it doesn't tell you how to. It's an optimization, it's specification. It's an optimization objective. Find something that minimizes this, but I don't tell you how to. And the problem is that in most cases, it's going to be very hard. Furthermore, if I want to go over all computable programs, this is not computable. But that's advanced. Right? So it's not a program, it's just a specification. What are you? Okay? So let me mention just a few. I mean, I am opening to hear questions. I don't know which order are we going to do it. I want to mention a few more topics and also answer questions. So I think the first topic that everybody or most of you have on their mind is what is happening with deep neural networks? Will they solve all the problems? So the first thing we already know is that if we analyze the sample complexity of learning deep neural networks, we cannot allow a network that has more edges than the sample size that we have. In practice, people do it. People use networks with tens of thousands of edges on just thousands of training examples. And the reason it works is, again, that our bounds are worst case. Under the worst distribution, such a structure will not work, but reality is not adversarial. Reality is not worst case. And one of the big challenges that is facing both machine learning and complexity theory. I mean, we developed complexity theory and machine learning for the past 50 years or something, but all we did was analyze worst case. And we realized that reality is not worst case, and we have to come up with notions that capture realistic situations, and we don't have any. This is one of the bigger challenges. If you look at what is happening in complexity theory, I mean, I don't know how many of you studied, NP-hardness, the complexity of SAT. The most difficult, notorious problem is SAT, but it used to be that if you want to say that your problem is hard, you say my problem is hard because I can reduce SAT to my problem. Nowadays, when you want to show your problem is easy, say my problem is easy, I can reduce it to SAT and so send it to a SAT solver, because they're very efficient SAT solvers. Now, SAT is NP-hard. How come those SAT solvers are so efficient? This is because the formulas or problems that you see in reality are not the case, and we don't have a good description of what you see in reality and have a theory to adjust. All we have is those worst cases, both in terms of sample complexity and in terms of computation. So that's my comment about deep neural networks. In the worst case, they can be terrible, they can overfit, and there are experiments that show it, that if you feed it with non-natural data, you can completely confuse any deep neural network. The reason they work well is that natural data is more tamed, but in what ways is it tamed? We don't have a good formal definition. So that's one big challenge. Other two challenges that I wanted to mention before we'll have like 5 minutes for questions is one challenge, the two challenges have to do with the way that now machine learning is being applied to more and more applications, and applications that concern humans. And this is very different than the statistical guarantees. So for example, if I want an artificial intelligence or machine learning program that advises judges on a verdict, and people use it in the US. They have a program that the judges use, puts in the parameters of the accused person, and the program calculates and tells you, oh, this person is very likely to commit a crime again, send him to 20 years. And this person is nice, and we can forgive him, and just say no, and release him, right? So people rely on such programs. But the guarantees that we have for machine learning are not good for them, because the guarantees are statistical. So the person that is being sent to 20 years in prison based on this program, it doesn't comfort him to tell him that, the probability of failure of my program is only 1 in 1,000. So yeah, you're going to spend 20 years in prison, but you're only 1 of 1,000. Don't worry. It's not good enough. So the kind of statistical guarantees that we have, and the same with programs that are used for autonomous cars. We don't want to get hit by a car that's autonomously driven and get the comfort that, oh, it happens only rarely. So we need some other types of guarantees. We call it safety, which is not the same as statistical guarantees. There are situations which we want to avoid at all costs. We're not happy with just epsilon delta, or if we have a program that drives a plane. Another big issue is fairness. People are using programs now to decide whether you can get a loan or don't get a loan. You apply to university, they use a program to predict how likely you are to succeed, and then they decide, did you get accepted or not? Turns out that those programs are relying on past data. And if in the past women were not doing computer science, it's very easy for such a machine learning program to say, oh, that's a wonderful parameter. If it's a woman, then I will predict she's not going to be a computer scientist, because that's my past information. And we call it violation of fairness. And there's a big drive to try to understand what is this notion of fairness and how much accuracy and precision we are willing to sacrifice in order to enhance fairness. And the last item that I want to talk about, which is relevant to both of them, is interpretability. If now we let computers, programs, machine learning, make decisions that affect our lives, we want to be able to ask, how did you reach this conclusion? Maybe there was a mistake. Maybe one of the parameters that you took from me was misjudged. So we want our decisions to be interpretable. And this is another big challenge. Because when you run a neural network and you get a neural network and say, oh, that's what I fed here, that's the answer that I got, what can I do? It's not interpretable, and we need this interpretability in order to be able to appeal against it, in order to be able to see how much are we willing to go along with the decision of the machine. So those challenges, making models that reflect real situations and not worst case, giving guarantees that are safety guarantees and not just statistical, taking care of fairness in machine learning, and having interpretable decisions of the machine learning programs. There are big challenges that we have almost nothing to say about, and they're important, very important. So if you're looking for something interesting to go into research, there are big challenges in those directions, and I will be very happy to hear about any ideas. Thank you very much. Any questions?
You previously mentioned that support vector machines have the C dimension. What does it mean in practice? Should not use support vector machines and kernel-based methods, or?
So it means in practice that you have to be careful. If you fix your kernel in advance, then we have reliable guarantees. Kernel is a big expert. But if I want you to search over kernels, then you have to be careful about not over, because by allowing you to see, I tried this kernel, it didn't work well, let me try another kernel, and so on, you can run into all. So you have to use this type of guarantees, this type of structural risk minimization, to somehow make sure that you balance the search for a kernel with the outcome, the performance you get. So that there are precise guarantees, but they are more delicate than the use. Okay, they're all happy. We know everything you wanted. Thanks so much.